Alright, it's the next day. We continue. And so what I thought would be the reasonable next step would be to take apart this guy and see inside the motors, see in fact if we're seeing gear damage. Because the other thing I figured was we have some spare motors. Right, so we have 3 spare motors. So we could just keep throwing motors at it. And they keep breaking, but we can get some runs in there. Sorry, I don't know if you guys can see those now. Yeah, so that could be one approach, but yeah. I am much more interested in building something robust. So, so for starters, you can't see the screen today because I think, or right now, let's not say today, because I think on this first part at least, we're gonna focus more on taking apart the motors, which will take not too long, and after that we can maybe you can do some computer work. Let's see. So I wanna remote SSH into the Raspberry Pi here. I don't know if you can see the password. Camera starting right at the keyboard. Okay. Seems to have failed. Not sure why. Okay. Sorry, I'm just getting into the file. So just get into the place where we can run the motors. So we can define what is it that I think is wrong. And it's just basically the noise and the fact that the robot makes a noise, the motor doesn't spin, right? So they should run the motors. Alright, so robot is done running. And of course, no load condition when I'm lifting it and there's no friction in the wheels. This can be fine. This way, the other way. So this makes me, what this tells us is that the teeth on the gearbox are not completely stripped, right? Because if they were completely stripped, there would just be no torque. Even at this low load condition, it wouldn't work, and it obviously works. Now, as soon as I put some load, well, today it's working great. See that one there, you can see, it's hard for you to see maybe. This motor here was just trying to move and it just, like you can hear it. Yeah, okay, for example, this happens at the extremes, right, and there's more load. So this wheel is probably almost full speed, and if I'm gonna put my finger here, wheel doesn't move, motor's going crazy. But then it becomes stuck, right? And I can, when I put my finger here and it stops spinning, I can feel the motor still spinning. So yeah, trying to understand how that happens. It's almost like there's a clutch that slips. That's not what's happening here. Yeah, so let's stop it for now. So that's the thing I'm trying to figure out. And today, the thing was kind of like standing up. Yesterday it was really bad. So I don't know, figure first step would be to take apart a healthy one, so we know what it should look like. Let's see. I think it's just 2 screws here. comes off. This feels like self-tapping screws going onto plastic rivets. Okay, so that's off. The thing doesn't come off yet. I think this other plastic piece might also be holding things together. It's like a rubber band, this thing. So we take that off as well. So that's off. This guy comes off. Alright, so this guy is the motor, of course, right? DC motor, brushless DC motor with a spur gear on its shaft there, right? And so no problem here, or I imagine there's no problem on that gear. It is a plastic gear, but these are pretty low torque motors, so to be expected. So I'm sure this is not what's broken. And again, if this is the pinion that's stripped, we would not be seeing the wheel spin even at no load conditions. I suspect the issue is here in this gearbox. So I don't see any more screws, so I imagine there's some snap features or just like a press fit. And it comes right off. Of course, remember how it works, right? So pinion goes here and both sides here spin. So there should be a shaft or two shafts. Okay, so you see first here, metal shaft there, or something acting as a shaft that retains two sets of gears. I didn't quite see how was this all assembled. There is some amount of lubrication to be expected every time you're working with gears. And yeah, then you have this plastic shaft, the two shafts for the wheels, and then these are actually multiple parts. This guy can rotate freely here, but then this guy is fixed on the shaft. So this rotates, this is shift, and it's all lubricated. There's some lubrication there. Now how does this engage? So you can see when I put it here, the big one is engaging the small one there, and then I imagine this other one will go in here like so, and so the wheels spin and they're engaging there. Now where does the pinion go? The pinion goes in between the middle, right? So I expect the pinion, maybe I'm wrong, pinion should rotate and move one of them around. So maybe I installed this wrong. Could be like that. So no. I definitely installed that wrong, but that's still not how it goes. Whoop. Let's try it again. So we have this guy. So the pinion guy needs to be meeting this guy here, because this guy has gears in this direction. It's the only one that has gears in that direction. That will engage with the pinion. It's funny how the cameras just stop working. Today we're using a two iPhone setup, and one of the iPhones, the one in front of me, is connected via Wi-Fi, and I guess the Wi-Fi, I don't know, it's like unreliable or something. Anyways, doesn't matter. You don't need to see my face. Yeah, so again, this pinion goes here. This gear is going to be this direction. These teeth are going to engage with it. I can already think these plastic gears here, that's what's gonna fail. Like that doesn't seem robust. But let me see if I'm missing anything. I don't think anything else can engage the pinion. Yeah, that must be it. So let me see if I can put this together in a way that works. So it's not that way. Could be this way. It's not this way. Okay. I think it's gonna be this way. I'm just trying to mesh the gears correctly. But it seems like it's not that way either. So I broke it and I don't know how to fix it. I don't know. Do we just take off another one? Take apart another one? Like the way the gears wanna fit just doesn't make sense to me. I'm gonna start with what makes the most sense to me. Okay, maybe we're getting somewhere. I don't know how this fits. Yes. I mean, maybe. Definitely not. Oh, I see. I might have had things upside down. So. Yeah, I guess the parts, the casing parts are not really symmetric. They look similar, but not. They're not. It's wrong gear. Yeah, this gearbox doesn't seem very robust. So when we take out the other one, I think I already know. It's a gear that meets the pinion. That's the one that most likely has failed. But I can't seem to put this together. I see where the issue is. Okay. This time we actually got it. Oh yeah, there it is. Nice. Little refresher on gears. Alright, so we close this guy. So that's for gearbox. Motor comes here, spins, and then oof. I mean, it's horrible. It's not nice. Basically, yeah, basically we have see if I can show you without destroying this thing. Oops. I'll try to give you a close up. Again, cheapest gearbox in history that money can buy. But okay, so this is the gearbox. We have a question. Motor with pinion. The gear at the bottom, like this one here, has teeth going up, this way, like up. Because this pinion goes in here and it meets those teeth, but only those teeth going up, right? And so we have poor engagement there. It's all plastic. And yeah, well, there is some amount of press fit there, but the interface is just not very good. So it's very easy to slide. Any inflection on that little gear, this like starts to slip. And that's why when we're seeing, we see the wheels spin at no load conditions, but then when there's any amount of torque, it just makes an ugly noise and it keeps moving, but it just, the wheel doesn't move. Most likely because this guy is spinning really fast. But since there's so much load on the gearbox, that gear is not spinning, and with this guy spinning, basically it's just spinning over the teeth, and that gear is probably just deflecting out of the way because it's so flimsy. So I think that's what's happening. But it was good to take a look. I want to bring some paper towels because a lot of lubricant. Anyways, so now we know that, but let's just go take one apart just to make sure that's indeed what's happening. Because this is only my theory. I mean, I think we can go over some examples later, but I don't think we need. This is a pretty actually kind of clever way of securing the motor to the gearbox, like this with this like rubber band thing. I was gonna say I'm not sure we need a gearbox. I think we can go direct drive for this application. All right. So this is our good motor. Should be installed. I can speed it. I can over torque the gearbox with my hands. I can do all to feel that, but yeah. Yeah, I was gonna say, like, I'm not sure we need we actually need a gearbox for this application. Direct drive is probably just fine. Now, this was a while ago, but I do remember when I made these brackets, everything has nice locating features and it's really nice. So it's nice to work with things that I don't want to say design well because I'm of course biased since I made it. But I mean, it's not, let's put it this way. It's nice to work with things that come together easy and in easy predictable ways. Is it? So the gearbox has some holes here, and then our chassis has these dowels, and everything just fits in there. So that's nice. I think for these, I might turn the power off. I won't turn the power off, but it's easy to not short anything here. Just in case we want to run the motor. So again, we take these apart. We cannot fully undo the motor because the wiring was soldered straight. There's no connectors. But I mean, that's just the motor design there. But everything else is the same, 2 screws. Another screw. And then we should be able to just pop it. Oh. Okay, so the first thing I would say before we take apart the gearbox, the motor pinion here shows what I would say no signs of damage. None of the teeth, all the teeth are still there, and I don't see any, any dust, like the plastic has been grinding or anything like that. So the pinion looks good. Onto the gearbox. This one's a little harder to take apart than the other one, but it could just also be a skill issue. And very similar to the pinion, I'm seeing full teeth here. No signs of things getting destroyed. No signs of damage. So again, I think my theory is still that when you put too much torque, the motor is able to skip the teeth here that meet the pinion, and just kind of like deflect this out of the way. Or just jump the teeth somehow. I would love to see that because I actually have a hard time believing that's what's happening. Because everything here feels very solid. As I push with my screwdriver, it's not like I can, actually you can really deflect it out of the way. So maybe I could see that happening. Yeah. But I don't know. The fact that there's no damage makes me wonder whether we can make these work by just essentially limiting the speed of, telling the motors to be more gentle, the motor controllers to be more gentle, limiting the speed of at which the motors are spinning. So we could try something there. I want to reassemble everything here. I think we're done with our science experiments. Okay. Every time in my career or life as an engineer that I've asked myself, does it matter? The answer is always yes, it matters. Does it matter is a terrible question. Everything, although like of course it's a natural question to ask. because I asked to myself, almost challenging myself, because deep down I know the answer is yes, everything matters. But it's like, really the answer, the thing I'm trying to answer is like, how does this matter, or why does this matter? I'm just gonna put the robot back together, and the one thing is that I think if we were to limit the speed of the motors, we would have to tune again the PID stuff, like the KP and the KD value. KP and KD, yeah, I said right. Alright. Alright, so let's jump back in the terminal. I'm gonna clean this around a little bit. Let's give it one more chance with some software help and see if we can make this work. And if it's still doing nonsense, then I'm all for getting new motors, and then we can spend some time looking at what motors are out there, what can we get, what makes sense, because I think I'm done. First of all, it seems like for neural network training, it would be nice to have encoders, so we can get some of the encoders. And second of all, I think I'm done with the work with the cheapest hardware possible, just because at the end of the day it always becomes the excuse for why something didn't work. It's like, oh, this broke, something basic. So maybe we get two motors that are nice, that we can rely on, and we do like a Mark II or a V2 version of these. But alright, give me 1 second to clean this around, switch the cameras and so on. Alright, let's see. Let's take this to cursor. So I'm remote station to the Raspberry Pi here, and this is a code that was running. I still can't drop my mouse. It's very annoying. Okay, so that's what's running. So I'm gonna say I want to create. Oh, actually, I'm gonna try to dictate. I want to create an alternative file to pid.py where we limit how fast the motors accelerate, period. I am looking to protect the motors from accelerating too fast, as when we accelerate too fast, the motor gearbox strips. How can we do this? And will this require retuning the PID values? Let's see. Well, let's start there. Maybe we should have done planet mode first. Alright, let's see. While the AI works, so we have read word, IME register, set motor speed left, max spin, okay. it's like a bridge, I think. Exploring how they are implemented, so you can recommend exploring, checking how implements slew limiting and whatever PA plus microcontrollers directly, noting PA plus PA output directly to PLM with no ramp. Slews only keyboard drive, not balanced output, creating PA slew with. Okay. So it's creating a new file slew. Ramps command PLM towards the PID target each loop, so wheel torque changes gradually. Okay. And then we have a new variable called motor slew rate. Full motor slew rate, max change in normalized speed per second. Scale 0 to 1. 2 equals full throttle in 0.5. 1 equals full throttle in 1. Alright, here's the explanation. A large steel error can drive PLM 0 on set that storks back when no set too much top speed. How to fix slew limiting. Okay, motor slew rate, max change to normalized speed per second. 0 full and 0 motor slew rate. Snap. Okay, and then motor slew reset on fall. Snap applied speed to 0 when the robot falls. Snap. Okay, so if the robot falls, motors go to 0. Makes sense. Don't need to full retune. Slew limit, add actuator lag to the PID, ask for more torque than the motor sketch. Balance can feel slightly softer. Keep smoky direction. Okay. I guess I want to say, help me understand how the motor slew rate variable works. If 2 equals full throttle in 0.5 seconds, and then 1 equals full throttle in 1 second, is this essentially a denominator? Question mark. But okay, and let's see how it's implemented. Let's see. So it implemented here, move forward. So it's a new function called slew toward current. It has a current, target, and a max delta. Delta, move forward towards target by at most, okay. Okay, and then we feed that back into here. Motor slew, these are the print statements, okay. Motor speed applied, 0, 0. If motor slew, that's the full commands. So motor speed equal used to be that, now that's motor speed desired. Now we added max delta, loop time, motor speed, okay. Slew toward. So it all comes back to that slew toward function here, which is the delta between max. Delta equals the maximum between max delta, mean, and the minimum between the maximum between negative max delta and the maximum and the minimum max delta versus target minus current. Per loop max delta, that's 4%. Per loop. Okay. Examples motor slew rate, denominator for time to full, distance for rate. A higher slew rate, faster ramps, shorter time. So why don't we start with a lower slew rate then? And then lower slew rate, and then we run these. And I do realize you might not have the best seat for this, but oh, typo. Alright, so this is me mimicking full vertical, and then it's like you tilt. Actually, I made it pretty fast. You can see there's some lag, right? I'm trying to get you guys to be able to see the ground here. I mean, yeah, obviously, okay, that's like, now you cannot stay upright. So it can, I don't know if you guys heard that, but it can still hurt itself by locking, it got in a position where it's locked. This bumper was locked into the ground because I guess it's a sharp corner, so we should round this, and it was locked into the ground and the wheels couldn't get it out. So it can still hurt itself just by just in new ways. It's finding new ways to hurt itself. And this is pretty funny, right? But this is what happens when you add so much lag to it. So let's increase the motor slew rate to 2. And then let's see how it reacts. Because right now it's a little too laggy, I think. Yeah, this looks a little more snappy. Looks like it can balance itself. It's like a little drunk maybe. I can still hear the motors sometimes. The gearbox like maxing out basically. Yeah, okay. You know what, guys? I don't know. I just think the gearboxes are just not good enough. Oh. It just tried to jump off the desk to relax. I mean, it is funny because it's standing on its own, but you can hear the motor is spinning, the wheel is not spinning. That's exactly what we're trying to avoid. And it's like, it's not just about acceleration, right? It's also about positions where the robot just gets more torque on the wheel to move, and it's just this gearbox combination is not able to provide any torque, essentially. So let's just say that we don't need we need more torque. That's what we need. We don't need a fancier gearbox. We just need more torque, guys. I want to stop this. Yeah, so we just need more torque. But in general, I think the idea of a slew rate is also good. Also makes sense. I wanna save this code, upload it to our all the code I uploaded last night. I want to upload that one because it's not relevant to the training conversation. But yeah, I think that's the end of playing with the robot for now. Let's see how we can improve. But also let me just see here, because we have some planning stuff from yesterday that let's see if I'm not sure if I want to lose here. Let's commit. Yes, this is done. I just think I'm just gonna close everything. Let's bring back our thing here. So 27 May 2026, took apart gearboxes, found no damage, but overall design doesn't inspire confidence. Seems gearbox not robust enough to transmit any meaningful torque. At least we don't have to worry about overheating the motors, because the gearbox will never allow for that to happen. So next steps, find better motor gearbox / direct drive. So I think this is what we should discuss. Yeah. If we are doing full rebuild, new microcontroller, question mark, right? So there was like a is it called a milk view? I think it's by these guys. Products. I'm trying to remember. It was something like this that had both wireless, Bluetooth. I mean, this has all of that stuff. We could use something like this, I think. $10. I need to check. In fact, give me 1 second. Alright, this is what I was thinking about. This is a microcontroller I was thinking about. Maybe I'll take a closer look later. I'll put it here. But also the milk stuff here, we're looking at interesting stuff. Okay, so it's totally possible to upgrade the motors, right? So this is what we have right now, right? So if we were to make a V2 version of these, V2, right? So we want to replace this guy, needs to go. And then honestly, if that guy goes, we probably get a better controller. Let's say the Raspberry Pi goes also, because we like it. We like to be able to remote SSH to it, but we don't like how sensitive it is to brownouts. So whenever we get rid of that, we could keep the back converter, but we need to keep the back converter, so that's not going away. And then we can keep everything else. And so for the motors, I actually have my Gemini agent. This guy. Yeah, so there's this guy on Twitter that I like. He goes by Homemade Garbage. He's Japanese. I don't know what's with the self-deprecating humor, or if it's even humor, but he calls himself homemade garbage, or homemade garbage, sorry. And so he spilled some cool stuff you can see here. A lot of balancing stuff, right? So this one balances with three wheels. You can see he stacks the things, just scales the same. I think this is pretty cool. And then he's done a lot of work with self-balancing robot, right? So for example, that one there. I don't know what any of this is saying, actually, it's translated. Reaction wheel, inverting, so it's still an inverting pendulum. He's also apparently using AI, he's using codecs. Inverted pendulum with a single wheel, I think this is what we're looking at here. Please translate. I like his work. This is good work. Yeah, do we need two wheels? Yeah, you do need two wheels to rotate, right? His center rail looks pretty good. His name appears to be Hona. Yeah, so what motor did he use? He used the Codec Sensei. Oh no, sorry. That's how he calls his AI, the Codec Sensei. But there's the air rates in the mediocre model and the actual machine are smaller. It would be more comfortable for him to work. So we'll consider improving the accuracy of the motor model. The motor used in the motor panel is parameter match based on the actual machine operation log to reduce error. I chose velocity actuator because I control the rope stride in speed mode on my actual device. So rope stride is it's a good brand, popular brand, right? So let's see. $100. See, I thought I was saving money by buying cheap, and it doesn't work, and then you gotta still buy $100 motors. So okay, website's like coming off a little broken. What did he say? He said rope stride 5. This is the one. Website is completely broken. Okay, 5.5 millimeter peak load, easy development. This is a torque speed under 48 volts. 48 volts. Wow. Is he meaning 48 volts? I don't think we have 48 volts anymore. We have a 6S LiPo. Yeah, we don't have 48 volts. We have to step up. This is good. I like the math here. Maybe I should get inspiration about that. This is a schematic. Very funny. We're basically doing very similar things here. LiPo, 3, Japanese stuff. Okay, well, 11S buck converter. Boost, DC. Oh, he's stepping up. So he has a boost and a buck. And he fits everything in there? Because my converter is huge. Okay, maybe I need a new converter too. Next change shows more further fat rope stride to control speed my speed. Okay, a big mistake. The code I liked is 2.5 doubts about whether past opening traction are being referenced. It was too scary to ask. Okay. I do want to know what converters he's using because everything looks so clean. Boost DC. Okay, he's just reading from the what's an atom matrix. We're doing competitive analysis here. It seems like this is his IMU. So exactly the same sensor. The main control loops. Okay, package solution. I mean, interesting. I want to make a new slide here. Or I want to write it here. Oh, sorry. What did he? Homemade garbage. And I'll link everything here below. Sorry, like in the video description. So you have this, but motor IMU. Yeah, I just wonder, okay, so you can see here's the electronics, obviously that's the battery, and on top that big block, white block is IMU, pretty sure. That's what that looks like this same thing here. Or is everything else? Where is everything else? I don't know, maybe that's not the complete assembly. Here's one more page. I'll be curious if there's like a tiny boost DC-DC that we can use. I mean, of course, there seems to be something else on the side there. Here he's more focused on I think he's doing PD, right? A physical dimension was previously invented reinforcement. It was produced during it was produced during the See, there's a seam to gap simulation. In simulation, the wheel doesn't move, but in real life it does. But okay. The following controller drives the wheel motor Mujoko, which you adjust exploration in KP, KD, KW. Okay, so it looks like he was basically he wrote code to optimize his PIDs on Mujoko. That's how I'm interpreting this, which is a good idea, right? I still don't understand. Okay, he has other inverter independent projects, but I still don't understand his power electronic stuff. Like, how is he powering everything? Here's using some other type of motor. That's a servo. He's not using a servo. You see, he's using servos apparently on this one. You can just do things, guys. Here the motor interface is made by, okay. I guess he's just using the motors. He's using the servos. I guess that, I mean, I don't know, the servos being fast enough, maybe. Power supply. The controller, oh, so atom matrix, it's not just an IMU, it's a controller. $30 of AliExpress and 5 stuck. Okay, out of stock. Does this do any power? Power killed it. Yeah. Okay. Includes development features. I need to like a data sheet or something. Built-in battery. Wow. Input voltage 5V. Okay. It is interesting. Let me update the notes. IMU controller plus IMU. I guess it is interesting that you can get so much functionality of your controller, right? So yeah, MicroPython, and you have a battery, and it has an ion view. I mean, that's nice. And it has a button. That's nice. And then on this one here, this inverse pendulum, this guy was just using dynamic cells. Where is it? I mean, this is another popular brand. I have, I think I have only one of these. Motor servo. It's just interesting to see what other people are using. By the way, here the motor is made of Fitec URT I used. Shoot, for the other build, I don't know what motor controller he used. I don't know if he said. Bloomberg transportation. Want to see the inverted operation. So I made an inverted pendulum. Finished. Battery. I wonder what this board is on the side. Power supply, controller. Semi-double communication circuit. And then a self-made interface. So okay, we already know that. So I guess you made that one? The substrate was raised using the circuit as reference. And so that's getting power there. It's talking to the microcontroller. And it's also talking to the motor controller board. This is required, I guess. Do you need that? That looks really good. Yeah, it looks really good, right? He says speed mode is better if you can get a good speed controller, but this time I couldn't get a good controller. Since it's a servo motor, not a so small gear ratio, there must be a delay in the response after detecting rotation. I mean, what's wrong with it? I mean, yeah, I guess to me that seems really good. Conclusion. Yeah, well, it is said to be the best in. Oh, now it's said to be best in crew control mode. I guess with his current setup. I'm already running. It is no match for the BLDC. It is no match for the BLDC brushless DC motor. Although the aircraft itself is also light and lightly loaded, which contributes greatly. So I think he's saying that BLDC is better. I don't know, kind of. I feel bad for those servos. Right. Okay, so this is the BLDC build, I think. Oh wow, there's infinite amounts of content here. Oh, what are these? I mean, we're not gonna be getting those, so. But he did link a previous page. Okay. Well, this guy has been experimenting with balancing stuff for a little bit. For years, actually. 2021. There's layers to these. So he kind of like just keeps, I guess, perfection or recreating the same thing but with different pieces. They're all different. I think he sells them actually. 2026, 2026. Okay, these are all 2025. These are all very. So he's really very much still into inverted pendulums. Yeah, this is great. Let's see what's going on here in the meeting. Okay, it's harder getting more real here. See, what are those motors? The motor is power supply, 3-cell LiPo controller, PS per controller, silicon. Okay. Supply, 3 printed housing. I'm assuming that thing here is his motor. I don't know what here. He keeps referring to it as an aircraft, but I think that's his Google Translator, whatever we're using here. Let me Google these. They're sold in Google, in Amazon Japan. Okay. I mean, yeah, maybe like I'm being too picky, right? Like anything like will do, like, yeah. Any motor, just give me any motor. That won't break. Oh, look at that. Those are my motors. That's not an inverted pendulum though. Okay, interesting. The other thing I'm noticing here is like these are all like way lighter, just because like they have a smaller battery too. So lighter, those motors they could put out less torque. This is the worst looking inverse pendulum so far. His conclusion. It is a bit difficult to achieve an inverted pendulum using this motor. It's not fast or responsive and has a lot of backlash. If you're using it with a DC motor, I think a direct drive would be better, even though it's a torque disadvantage. I mean, didn't we reach the same conclusion? That's good. Well, now I use BLDC vector control to spin it around. I even put in my feet. Yeah, that looks good. BLDC vector control. Gonna look for that. Let's see what else. In the first generation, plus pin had a high current capacity and could also drive a DC motor. The motor could not be driven with it was shut down, possibly because of the turn-on protection function. Therefore, the BAT pin is used for motor supply. Oh, cool. So that board can. The 5B DCC is more capable than the original DCC, so it seems like a waste, but it's not. It's not the 5V used to drive motor, so it's unavoidable. In fact, it can be said that the original was also driver was not as good as Quad Central. I'm a little confused. Just I think the translation is just breaking stuff. But what's cool here is like this guy seems to keep finding controller boards that can serve basically multiple functions. So this one was even powering the motors apparently. He did say the BAT pin, the battery pin, right? The battery pin. I guess he has a built-in battery, that's why. Interesting. Yeah, I guess I need to try more of these type of things. Brushless motor servo 7. See, now we're going back in time. It is really cool to see how far back this guy has been working on. Sure, let's open one of these. So he seems to be doing direct drive for most of his stuff. That almost looks like a drone motor. Yeah, just don't be picky about the motors, right? Just get something decent, yeah. I do wonder what motor controller he's using, but okay. I think I have some ideas of what to order now. And so what we're gonna do is we're gonna order more stuff. Oh, and I guess the other thing I wanted to show was possibly where is it? This guy. $90, a little expensive. A small low power microcontroller board which allows you to easily implement applications using machine vision and in the real world. Yeah. I mean, okay. Not sure if we need all of that. I just thought it was cool. It has Bluetooth, it has Wi-Fi. It has a camera. That seems pretty cool. That seems like, I don't know, could be handy. And then of course there was like the milk stuff. I'm not familiar at all actually. I've used one of their things, but I don't know which one we would want. This just seems so cheap. I need to look more into the microcontroller part, but yeah, if we could just get something that allows us to remote SSH into stuff, so we don't have to reset full rest R.I.P. And then if we could also get rid of, well, we'll always need some sort of motor driver, I think, but you know, maybe something better. And if these two boards could be the same potentially, yeah, there's some opportunities there. But yeah, like I'm gonna keep doing some research, and we'll just reconvene next time, and then because I'm gonna order the parts, it's gonna take a while, you know. So, yeah. So for now, we're gonna retire this guy. You know, we're saying like we took our lessons, right? The motors, we think we can do better. We're gonna do better. I think inverted pendulums is an interesting shape factor. So. I think we can keep investing a little time, a little money on it. So yeah. Anyways, until next time. Thanks for watching.